Unmute. I've got some sound, so oh, there's 6 already. So I don't know how many people we're going to have. It might be a lot.
One of my best purchases I've ever made. $64 for my warranty, and it's never failed me. I think I've had over 100 pounds on it. Pockets are not afraid. It's fun. At least one
mute them. 17 is not the same number of people. I was afraid we'd have 200. And that might still happen, but maybe not. We're more or less on time, and I got 17. Well, that's no big deal. And I don't know if the system might be able to handle 200. So you people logging in over Zoom, if something is horribly wrong, use the chat to let me know. That pops up and I can see you. One weakness of my system is I cannot see what you are seeing. So if you have no sound or no video or somebody's dog is barking or something, send me a chat so I know. Because this is all amateur stuff, done with amateur tools on my laptop and not terribly good. Privacy, please. Aha, a chat message. Everything looks good. Okay, thank you. Good, glad to hear it. Good. So, all right. I'm not gonna actually start the lecture for 10 minutes yet. I like to wait until 10 minutes so the people have time to show up. And when I'm waiting, I like to talk about the news, so I'm gonna do that. Here's the news that I've noticed. This one was pretty important. And so is that one, actually. Yeah, it's not that exciting. This is interesting, however. That. And all right, well, here's a few news things that might be interesting. A student told me about this and I looked it up. It's true. There is some law in the United States requiring a new driver's license for everybody in California by 2020, or you won't be able to get on an airplane. Their new driver's license has to have some additional technology in it. So by October of 2020, we all have to get new driver's licenses or you won't be able to get on an airplane. So that's important to me and probably to you. This guy is a famous economist and he has become aware of the stablecoin tether. This is why if you have Bitcoin, sell. This is my recommendation based on no qualifications whatever. I have no ability to predict this stuff. I didn't think it should ever have gone up above 300. It went up to 20,000 and I was saying, this is nonsense. But anyway, now I think it has all come out. This thing called stablecoin tether is the scam that was used to pump the price up this high. They pumped the price from 300 to 1,500 with 2 accounts at Bitfinex. Up to 20,000. It's all fake.
I think if you go
to pump and dump scam. And so if you dump, you will be one of the people that pay for all the others. So right now it's still around 10,000. My opinion is it is going to fall to like 300 within the next month. And never, so get the hell, and when it falls, you will not be able to sell because the exchange will crash. The main exchange is the one in San Francisco, Coinbase, and they crashed 3 times in November because people were buying faster than the server could handle. And they set out a warning then, they said, you know, our servers couldn't handle a load from the buying. If you guys all try to sell, good luck. So it's gonna fall like a rock. You're going to try to sell, the server will be down, and you'll be crying in your beer while it falls all the way to the bottom with no way to turn your fake money into real money. So if I were you, I would get out now. But all the Bitcoin enthusiasts say, oh, it's going to keep going up to 100,000, just stay in, because they want you to stay in so they can get money. That's how pyramid schemes work, and that's all Bitcoin is a big pyramid scheme. Yeah.
Did you hear about that rock singer? 50 cents. He has 50 million or something, $5 million.
Yeah, that's right. He had some Bitcoin. That's trivial, and it went up. Yeah, but I hope he sells.
So what's going to happen to the Dow?
The Dow will not move an inch. Bitcoin is. That's why serious professionals don't care about this at all. The total capitalization of it is like $12 billion. It's a drop in the bucket. It's nowhere. It's not 1% of the economy. It's a tiny little fraction. It's a small number of lunatics playing a game with their money over here, while the real companies are moving real money. That's why all serious financial professionals are just sort of laughing at it and sneering at it. But now what's happened, which of course I thought when the truth came out about Trump, people were turning against him, and they didn't. I mean, it's very hard to predict how long people will keep being stupid. But it has come out, it was pretty obviously always a scam, and now the exact mechanics of the scam have come out. This is like Snowden. Everybody knew the government was spying on everything, but Snowden actually leaked the proof, chapter and verse, of exactly how it was happening. And these guys now figured out, they created this thing called stablecoin tether. They pretended it was matched to the dollar. Then they just printed a whole bunch of it that is not backed by a dollar, but they continue to count it as a dollar, and they're buying hundreds of millions of dollars of Bitcoin with it to pump the price up. So it's all a scam. It's a sophisticated pump and dump scam involving several different cryptocurrencies to make you think the price is 10 or 20,000 when it's not. And suckers that put their money in are just getting milked. And so anyway, it's if you do have some, for God's sake, sell. If it went up from 8,000 to 10,000, you made some profit, take it and run. That's my advice, based on no qualifications whatever. So anyway, and here's a couple articles that go through explaining how they did it with Tether. They pumped it up in November. That's why it went up. I was sitting here looking, why is a Bitcoin bidding for $20,000 when it's really worth 300? And it's because they pumped it up. Anyway, this one was interesting. You can inherit vulnerabilities from the libraries in your code. Let's see, I have a chat message. The email to contact. Yeah, that's the right email. See that 127, using the infrastructure app. Okay, yes, email to contact me about the course. Let me check and make sure that is correct. It's in the projects, which are down here. And here's a project, for example. I put it at the end. And yes, that is the email to send projects and questions about the class. If you want to do it by email, yeah.
Oh, sorry, you could finish. Sorry.
That's all right. Go ahead.
Well, I kind of noticed between the two Jasmines, the unoffensive one and the offensive one.
Yeah.
It worked for the offensive one, but not.
The unoffensive one doesn't work?
It didn't work well for me.
Oh, okay. I haven't. It's probably the older version. I have to update my inoffensive one. Thank you for telling me. I made that like 5 years ago. And I thought I saw another chat message, which is great. That's what I use. Okay, good. Good. Fine. All right. So that's a good question. Let's see if there's any. I still got 4 minutes. So let's see. I think there was still something happening in the news. Yeah. So the libraries, Vincent Taviso at Google has been debunking antivirus for years, proving horrible security problems in the antivirus products. And now he's found them in RAR and zip. What happens is these products use libraries, and the libraries have vulnerabilities, and everything built on them inherits the vulnerabilities, and this applies to antivirus products and also to RAR and zip. So this is 7-zip, which I use all the time. 7-zip has vulnerabilities it inherited from its libraries, so you can put a corrupted file, unzip it, and it takes over your machine. And that's pretty good fun, and we'll be doing that in this class, not with the particular 7-zip, but a very similar one is this one, Easy RM to MP3 converter that takes a media file and takes over your machine. Because it's another way to take over a machine, not a direct network connection, but you download a file, you run it into a program, and even though it's not intended to be a remote control program, you can make it so it exploits that program when you run it. So it's a similar kind of issue. And this one, people say is going to make a big deal. This is that you can now, there's an app you can download apparently for free that will take one face and paste it on someone else's body in a video and do it so well that it's very convincing. So they make fake porn with like celebrities on the bodies of porn actors, and they make fake political speeches where a politician appears to be saying something they didn't say and stuff like that. So they say we can expect a lot more fake videos coming out that really convince people that things happened that never happened. This used to only be experts that could make good ones. So Trump and his accusation of fake news will have more basis for that. They'll probably have a bunch of fake Trump videos soon and other things. So for what it's worth, it'll be a brave new world. All right. So we got 33. This is not bad at all. With 222 people signed up to take the quizzes. I wonder what would happen if they all tried to do the live stream, but 33 is definitely manageable. I've had that before. We should be good. Let me just mute them all again so that they're not having each other's barking dog or anything. And it's 9 minutes after. I think that's good enough. All right, so what I got today is we're going to do our first exploit. That's pretty much all it is. And that's all it is in your book too. There's a chat message. More people will be joining on advanced chapters, possibly, or maybe they'll just watch the YouTube video. I don't know, but that's fine. Here's chapter 2. Okay, so I just updated all this stuff today because Kali keeps changing everything and breaking everything. All right, and that is one annoying thing about Kali. It's free, so you can't really go yelling at them demanding service, but they keep breaking everything in each version. And the new version broke quite a few things, so I keep having to rewrite stuff. So this now works on the latest version of Kali. So we're talking about stack overflows. This is the classic exploit, the one that started it all, the Aleph Null paper from Frack about 20 years ago that taught everybody how to develop exploits, and all future exploit development is based on these principles. So here's the most popular technique, and the fundamental problem here is you have C, and C requires you to reserve memory before you store anything, but it does not check to see how big the thing you're putting in the memory is, so it is very easy to reserve space and then put in too much stuff. It is basically a design defect of C, and C is pretty much responsible for this entire category of buffer overflows. Other languages like Python and Visual Basic do not have this problem, because if you try to put more data in, it automatically resizes the container to make it big enough, but C does not. And C++. That's the fundamental problem. And you can see it with a very simple program. Let me bring this one up live. And I guess it's time to mention the annoyances. So if you get a Kali 2017.3 virtual machine, it is pretty messed up this time. They always break something. And this time what they broke is VMware tools. So when you install it in VMware, you will not be able to resize the desktop or copy and paste anything in or out. Now, that's very annoying because to do projects, you often want to copy in at least text and stuff. So I found a workaround and I put it here in Kali 2017.3 fixes on the page for 127. So before you start doing projects, project 0 you do with Heasman, which is fine. But before you do any of the others, set up your Kali machine, and this is what I would do to set it up. First, you can install VMware tools. It's got one version installed that doesn't work. If you install the other version, now you can resize the desktop, but you still can't copy and paste. So you might even just skip this. What use is that? Who cares about resizing it? What I decided to do is use SSH to connect to Kali. Then I'm in a window I can copy and paste text into, and that's good enough. So this, by the way, makes your Kali very insecure. So you certainly, for homework like this, it's probably fine. If you're going to be using Kali on like a real pen test, you'd want to do a more sophisticated thing than this. But all you do is install OpenSSH server, and then go into the config and permit root login, and then start it. And now your machine will be listening on this port on port 22, and in my case, it's even got the default password, root and tour, because I only use it in NAT mode on my machine to re-talk to another machine, so someone from the outside can't directly address it. So it's totally insecure, but it's on a somewhat isolated network. And I really don't care. I don't have any real company secrets to protect or anything, but be aware this is a really sleazy hack. But the result is now you can SSH into your Kali. So here's my Kali. And if I do IP address show to see what I've got, I'll see my IP address here is this thing, a local address ending in 235. And up here I did netstat -pant. It's a very useful command to see all your listening network ports. And I am listening on port 22 with SSH. So I can connect from a command line on my Mac here. And that is SSH root at that number, 172.16.1.235. It asks me for my password, which is tour, and now I'm in as root on my Kali machine. And I can copy and paste into this window. So this is what I recommend. Probably within a few months, they'll fix VMware tools or something, but there's no real reason to do anything else. Just treat it like a cloud server. I only want to control it from the command line anyway. So this will do. So once you have Kali working, you can now try some of these projects to see. So I have demonstrations here, and then there's projects which you'll do for points. So let's start with, get rid of this one. Actually, I'll keep this one and get rid of the other one. Okay. All right. So here's an SSH into my Kali, and I just want to make this fit on the screen better. That'll do. All right. So I already put this one on my Kali machine, and I should be able to open it. All right. So let's do CD 127, LS, and I think I called that chapter 2A. Let's try nano chapter 2A.c. Yeah, all right. And I'll get rid of the colors. All right. So what this does, this imports string headers and standard IO headers, so I can use a string object and I can use print. And then it defines an array with 5 elements, and it puts in 1, 2, 3, 4, 5. But those elements start counting at 0. This is array 0, array 1, array 2, 3, and 4. Then I print array 5. Now, a sensible language like Python or something would not let you do this. There is no array 5. It only goes from 0 to 4. But the way C works, C is just a very thin shell in front of assembly. So when you refer to array object 5, it just takes the address of array and adds 5 times the size of a word to it and prints you that byte. It doesn't worry at all about how big it's supposed to be. If it can find it, it just runs. It assumes you are supposed to keep track of where it is. So if you run this, I compiled it. I can just do it this way. GCC, come on. Okay, GCC minus O chapter 2A and feed in chapter 2A.c. That's how you compile it in the simplest case. And now I can just run it, chapter 2A. And I get this bizarre minus 107 million big number because I put in 1, 2, 3, 4, 5, and then I looked at data beyond that. And it just shows me what's in there. This is the problem with dangling pointers. Because now I'm able to read data which the programmer did not expect me to read. And this is one of the many memory corruption errors you'll get with C, and we're going to be exploiting. Now we can look at it in the debugger. And in order to put it in a debugger, I'm going to use -G. And by the way, I'm going to get in the habit of doing this. -G lets you debug it with symbols so you can see the source code. And for later purposes, there are 2 switches I want to add every time I compile, which is static and no pi. What those do is turn off the latest features that have been added in the latest version of GCC, which foul up everything in this course. With those 2 switches, it will compile things the old way, which leads to these easily exploitable vulnerabilities. Otherwise, it makes position-independent code, and it tries to connect to dynamic libraries, and both of those are cool, but they totally foul us up. We'll get to that stuff later. But right now, we want a plain, simple, compiled version that isn't going to have any complicated features. So I'm going to compile it that way, -G, so we can have debugging symbols, minus no pi to stop having position-independent executables, and -static to put all the library code in this file. So it is not loading libraries from other places, which are hard for me to handle. So that makes a plain file, and now I can debug it. GNU Debugger is your friend. It is very user hostile, but GNU Debugger is extremely powerful, and you're going to spend half of this course in GDB. GDB is how you see how the program runs. So the program is ch2a. GDB by default prints a long, irritating banner, and I get tired of seeing this. So to get rid of it, you use quiet mode, GDB -Q, and now ch2a. Now I just get the debugger. It read symbols. The symbols are not there in real viruses and normal code, but they're there in code you compile with the -G switch to add them. And if you have symbols, you can see the source code in GDB, which is very nice. So I can print list and I can see the C source code, so I don't have to work directly in assembly language. Most of the time, we're really going to work in assembly language, but for the first half of today, we'll use C source code. So here we are, able to see the source code. Now, I can put a breakpoint in here. Let's break before it returns. I want to stop this program while it's running, and so I'll put it at 7. So it's finished doing everything, but it just hasn't quit yet. I'll put a breakpoint at 7. and then run to that point. When I run to that point, it stops. So the program is still executing, but it's halted. And the reason I did that is now I can look at variables like array. So I can look, examine 10x. This will examine 10 hexadecimal words at the location. And the location I'm going to look is ampersand array, which is the pointer that points to the start of the array variable. So I can see what's there. And remember, here's what I put there, 1, 2, 3, 4, 5. Then there is other data, which is not part of array here, which is this long hexadecimal mess, and that's what it printed here in base 10. So I can now read past the end of an array, which is kind of nuts. So that's what this one does. All right, that read past the end of an array. Now the next thing, of course, is to write past the end of an array. So let's try that. That's going to be ch2b. I quit anyway. I don't care about finishing that program. ch2b.c is here. So this one just defines an array, defines an integer, and then writes 2,000 words starting at array. So there's only room for 5, but it writes 2,000. So let's run that one. We're going to compile it the same way. So it's just 2b. And then debug it the same way, gdb quiet ch2b. Now I can list the source code, and there it is. It's longer than 10, so I'm going to list 115 to give, there, that gives me all of it. Now I can decide, I guess I could stop here. See, if I stop here, it will only have done the first one. I want it to finish this loop and then stop here, if I can do that. So I think it's just going to crash anyway. Yeah, it's just going to crash. And yeah, we'll do it without a breakpoint. So let me get out of here and show you something first. Since I'm going to quit, let's just run it. /ch2b. It crashes. Putting 2,000 things in where there is only room for 5 has, as you might imagine, led to some kind of problem. So that's fine. This is the first step. The next thing is to understand the crash. So you do it in here. Now I run, and it crashes, and it reached a segmentation fault here at this instruction, and it gives me the C code. At the code that sets an item to 10, it was no longer able to set that item for 10. All right, now I can look at the array, x/50x, at array. And here's the A is the 10. I'm putting 10 in every word. Here it's going 10, 10, 10, 10. Some of it appears to have gotten overwritten by something else, but it keeps on going 10, 10, 10. And what happened, this is a non-exploitable boring crash. It filled up the whole segment of memory and hit the end of the memory segment. So this is not exploitable. This is just like bursting a balloon. You blow it up until it breaks. It didn't do something that let me control one of the registers like EIP. It just filled all the available memory and stopped. And that is a denial of service attack, but there is no way to turn that into a remote control attack. So we can't really do much exploit development on this crash. All right. So that's what it does. And you can see here, why did this cause a crash? And the answer is, you can see exactly why it crashed here. If you do info registers, this will show me the current state of the registers. It crashed on this machine language instruction. And I can examine the machine language instructions near there. Here's a command I like to use, x10i. You can examine memory in various ways. X will show it to you in hexadecimal. I will show it, the memory to you as machine language instructions, as assembly instructions. And then I can look at EIP. And if I do, I will see the current instruction and a few after it. I often want to see some instructions before it, so I like to do EIP -10. This is a little bit risky because I might hit between instructions and get misinterpreted stuff. But most of the time it works. So this pointer tells you the current instruction. It crashed because it could not execute that instruction. Now this instruction takes the immediate value 10, written as 0xa, and it puts it in this location. This is a location calculated by taking -18, adding the extended base pointer, and adding EAX and then 4. So it uses registers to get there. So the registers matter. Let's look at the registers and make my window a little bigger. It crashed on this command, and look at EBP is here, FF648, and EAX is here, 628 in decimal. It was trying to do 2,000 writes. It did 628 writes. And what happened is EBP plus 274 hit the end of a region of memory. And I'm not going to bother to bit down to the exact details, but you can, by the way, if you want to really get to the bottom of this, you can look at the memory map. We're not going to need it until a later class, but I'll just mention it here. It's info proc map. This is the memory map that shows you the segments, and you'll be able to see how it hit the end of a segment. And this happens in Windows too. This is the kind of crash you don't want, a crash that can't be exploited because it just filled up the memory. All right. And that's the game. See, the thing I look for here is the 0A didn't end up anywhere. I was writing bytes of 0A, and if I was lucky, they would end up in a register like EIP or EAX or something, and then I could exploit it. But it did not crash by putting my data in a register. It crashed by just using up all the memory. So there's no obvious way to get control of the machine with that. All right. So that's the game. It writes to RAM. We went so far we had a program. By the way, I mentioned before, here it is again. These are in the AT&T format. So it is immediate values here. Source is on the left. So here, for example, is a move. The way I always tell is by looking for an immediate value. This is the command that moves a 10 into that address. It cannot move something into 10 because 10 is not an address, it's an immediate value. So this is the format that is move source destination, whereas Jasmine is Windows oriented and it had move source destination, the other format, which is Intel. So I just mentioned that as we go by. Every time you see assembler, it could be one way or the other, and until you get good at spotting the subtle differences, I tell them apart by looking at a immediate code instruction. So here's Jasmine. You've been here before. We used it last time. That's using the other format of it. It is a good place to practice assembly code. So let's talk about the stack. The whole reason why the stack exists is for subroutine calls. That's why it has this funny last in, first out property. So here's the point. You have an extended stack pointer pointing somewhere, and then you push variables on and the stack grows. So if you push a 1, it will put a 1 here and then move the stack pointer up. When you push something here and move here and put it up, everything grows and then comes down from the top. So the last thing in is the first thing out. So that's what pop does. Pop makes it go down, push makes it go up. The extended base pointer is your pointer to the bottom of the current stack frame. And the ESP points to the top of the current stack frame. And there's frame after frame. Your operating system is using several layers deep in the stack. Then you launch a program, and your program makes a stack frame for local variables. Then your program calls a function, and that makes another stack frame on top, and your function calls another function. And you have layer after layer of function calls. And when they return, they pop a bunch of stuff off the stack and move EBP down to the next stack frame. This is the main process that we're going to exploit. So this command copies the data 16 bytes down the stack into the EAX register. It takes the EBP, which is the start of the current stack frame, adds to it to move into the stack, and then puts that variable in EAX. You'll see a lot of commands like that. This is how you fetch the value of a local variable in a subroutine. So that's the point of functions. This is the purpose of the stack. So when a function calls, when you call something like printf, or your operating system calls main to start your software, it stops processing instructions in the calling routine, saves the current state of the processor, the EIP, then moves into the subroutine, and the subroutine now has a prologue to set up its stack frame, use it. When it returns, it removes its stack frame and resumes processing in the calling instruction right where it left off. That's what's supposed to happen. So let's set up a simple example here and play with it. This is ch2d. Get out of this. Let's nano ch2d.c. Okay, so here, I'll get rid of the colors again. I have a main function. All it does is call function 1, 2, and then when it's back, it prints returns. And all function 1, 2 is bring in 2 variables and then define an array and not do anything. So it just sets up a couple of data structures and comes back. But we're going to watch how it does that. Okay, So first, let's compile with symbols. Oops, I'm gonna not save changes. All right, let's compile that like this. It's 2D. Okay, and debug it and list the code and put in some breakpoints. So GDB of ch2d. I don't need the dot slash. All right. Now I want to list 1 to 15. We'll probably do. Okay, there's my code. Here's the function, and there's main. So I want to put breakpoints at 9, 11, and 14, which is before we call the function, and 4 inside the function, and then 11 when we come back. You can B will put a breakpoint. So I want to put a breakpoint in 9 before we call the function, a breakpoint at 4 when we enter the function, and a breakpoint at 11 when everything is done, but we haven't yet returned to the operating system. Now I can run to the first breakpoint, which will be at line 9. So now I have started main, and I'm before executing this line. Okay. So now I look at the registers. And so notice the stack frame. We can make a note here, and I'm going to open up a text file and do a little diagram here. Let me get rid of this stuff, make a new one. Okay, and this, okay, make it big. So here's what happened. Right now we are in main, and EBP is this. Okay, that's the bottom of the stack of the main stack frame. Now I'm going to continue. Now I'm inside the function. If I now info registers, EBP is this. So this is the function called function. So 638 is main. Now I have a new stack frame, 620. It goes from 600 to 620 is the memory used by this function. When I return, it will move the stack back to where it was. So if I continue again, I'll end up back in main. And now if I info registers, it's back to going from 630 to 638. So this region of memory, 600 to 620, was used only temporarily while I was in the function. And when I return, it's deallocated and rendered available for future use. This process of reserving the memory, using it, and then resuming where you left off is the heart of all the attacks we're going to do. Perverting that process so that when it tries to return, it goes somewhere else instead. All right. So let's go here. That's what I wanted to show you. And we can also examine the stack, and let's do that inside function. So let me go in there. I'm going to resume, get back where we started. I'm just going to do run. This will reload the program. It warns me you're not finishing the previous execution. It preserves the breakpoints. So it stops it inside main before calling the function. Now I'm going to continue into the function. And now I'm going to do info registers. These single letter commands will often work. So the stack, this is what I always do. And this should be a habit. You do info registers. Now you highlight these two values. This is the stack frame, which is what we're going to be messing with. So it goes from 600 to 620. Now I want to look at those values. I just memorized this. X20X is pretty good. This will give me 20 32-bit words of data. And I start it at ESP. So this just starts at that and shows me all the data after it. Now I look up here and see where the stack frame actually ends. It ends at 620, which is here. So this is the word that starts at 620. And remember, it's kind of backwards. This is the byte at 620. This is the byte at 621. This is the byte at 622. And this is the byte at 623. So this is the 32-bit word that started at 620. So this is the stack frame. And that is super important. So when you're developing an exploit, you do info registers, you look at ESP and EBP, and then you highlight the stack frame. This really helps you understand what you're doing. And so this is the temporary variables defined there. And the last thing in the stack frame is the saved EBP for returning. And the next word here is the saved EIP. So if the programmer made a mistake and let me save too much data on the stack, I could overrun and change this number, and that number will end up in the EIP. So this is at the heart of everything we're doing. That's why I said get in there, you put a breakpoint, you do info registers, and then you do this, examine at ESP and highlight the stack frame. Now you're ready to develop an exploit. I know I want to change that number. All right. Now this program doesn't have a vulnerability, but our later ones will. So here's just a picture of a stack frame. So we've done that. All right. Well, I've talked about all this, which is fine. Okay, now when you first enter a program, a prologue runs, which is what creates the stack frame. And you can see it, by the way. I think I'll just do it here. Let me disassemble the function. You can disassemble things by name. Disassemble function. There's only a few lines of assembly code to make a function this simple. So it pushes EBP and it subtracts 20 from the ESP. That's why the stack frame had 20 words, 20 bytes. This is how it makes the new stack frame. It saves the old EBP and it moves EBP, puts ESP, the old ESP in the new EBP. So it starts the new stack frame on top of the old one, and then it subtracts enough room for all the local variables from ESP. This is the code that is called the prologue that created the new stack frame. Every function starts with a prologue, and what the prologue does is save the old EBP and subtract, move ESP and EBP up to make room for the new stack frame. And then you do your code, and when you return, it goes back to the calling routine, and that will undo this process. This return will pop the next value off the stack to end the current stack frame and take that value and put it in EIP. It'll pop the first one and put it in EBP, which is the end of the current stack, and then it will pop the second one and put it in EIP, and that will put you back in the calling routine. That's how it works. And if it seems a little confusing, you'll get used to it. And we're going to be using this for most of the course over and over again in all the projects. So that's the game here. All right. So now I've got 2E here, and let's play with this one. This one, I think is the same one. Oh, I got some chat messages. Let me see what they're saying here. All right. Move EBP to ESP and pop EBP is what leave. Yes, that's what leave does. Yes. All right, good. All right. So this one here is CH2E. Let me go out of here and see how that one looks. CH2E.C, I think it's different than the one we did, but not much. Yeah, this one just lets you see a printf down here where the return address points. So I just want to show you that part. So it's again, you have a main, it calls the function, and then down here is a print when it comes back. So let's compile that one, which is E. And then GDB E, and I can make it quiet. All right, now I can there are two functions. I can disassemble main, and here's the main function. And it calls, by the way, the fast way to read assembly code, like I said, think of a child that can't read and you just look at the pictures. Look for things over here. That's the name of the function. This is the put S that prints something on the screen. So you don't even really need to worry about anything else right away. This orients you. Then I can disassemble the function. And there it is. It again doesn't do much of anything. So I can also use the C code itself, which is the easy way. Let's do list 1 to 15. This is the raw code. So what I would like to do is see this instruction and stop while I'm in here so you can see the EBP. So I'm going to put a breakpoint at 6. And then run to that point. Now, I am inside the function, and let's take a look at the stack frame. So this should be a reflex action, info registers. You look at the ESP and the EBP. Now you do X/20X ESP. And now you can highlight it down to 620 is EBP. So that is the stack frame. So I'm in the function, and I'm going to resume at this value, 804-8868. That is the saved instruction pointer. Now, just to understand that, let me disassemble main again. And I'm going to make this all fit on the screen. That'll work. Okay, so this is the stack frame. That is the saved instruction pointer. And that value, 868, points to right here, which is right after the call. So it's doing just what you would expect. You call the function, and when it returns, it executes this instruction here, the next one. And the prologue and the return function rearrange all the registers so it's all ready to go. The registers are back the way they were in the original state when I come back here. So I can carry off ESP and EVP are back to where they should be, and EIP. So that's what's going on there. And I think that's all I wanted to show you there. That's the prologue, and leave restores the original stack with these commands, move ESP to EVP and pop EVP. All right, now we're finally going to make a program with a vulnerability. So all we do is start with the same thing we had and now add an uncontrolled read operation to it. So let's get out of this, and this one is ch2f. Whoops, got to have a space in that command. Okay, get rid of the colors. So all I've done here, there's a main function that just calls a subroutine and then returns. You don't want buffer overflow exploits in main because they're hard to exploit, because the process of returning from main to the operating system is more complicated. Let me check my chat log here. The videos, yeah, the videos will be on YouTube, yes. Good, all right, so so we're in here, we're gonna call here. Now while I'm in there, I define an array 30 characters long, and I do a getS, which will read from the user without any limit, and put it in array. Then I print the array and come back. So let's compile this one. Find my compiler statement up here, and this is 2F. Okay, and now if I just run it, the first thing you do is you fuzz it. You don't need a debugger at first. You run it, it asks me for some stuff, it returns it. Then you fuzz it, which means you put in more and more messed up input. So let's just put in a whole lot of A's. And now I get a crash. This is what you want. This is the first step where you fuzz things. You throw all kinds of junk at it until it crashes. Now you have something interesting to examine. So now you want to find out, why did it crash? Is this an exploitable crash or just a boring crash that isn't going to be into remote control? So you do that in the debugger. I run it in quiet mode ch2f. Now I'm going to want to examine the situation at the point of the crash, but I can just let it run and crash. That's one way to test it. I can do it before. I can put in all those A's. I'm going to copy and paste them. If I do that, it crashes. Notice right here, that is the EIP where it crashed, and that is AAAA. 41 is A in hexadecimal, in ASCII. So right away, I know I've got an exploitable crash because some of the characters I put in ended up in EIP. So that's great. That means I control EIP. Now I just want to get down to the details and figure out exactly which A's to mess with. So to do that, I need a breakpoint. So I can do it with list, 1 to 15. That shows me the code. So in this array, this gets is what caused the overflow. I read too much data into this array. So I would like to examine the situation after I read, but before I try to return. When it tries to return, it's unable to return and it crashes because the stored EIP has been corrupted. So I want to stop, say on line 8, after it's done the read, but before it tries to return. So I break at line 8. Now I run. I start it from the beginning. I put in that long line of A's. Now it has not crashed. It has hit the breakpoint. And now I can examine the memory with info registers. Just as before, I look at the stack. ESP is 600, EBP is 628. So I do my X, 20X, ESP. And 628, this is 620, this is 624, this is 628. So that is the stack frame. The 41s are the A's I put in there. They start here and go on and on down to here, and then they go past it. So someplace about 2/3 of the way through those A's, my stuff overwrote the EIP. So now I just have to find how to target it precisely. So to do that, I just need to use something a little more intelligent than just a long series of eggs. So for a simple case like this, I don't really need to do anything too much. Let's just run the code again. Yes. And then let's put in something less repetitive, like A, B, 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 C, 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 C. Let's see what that does. Now I examine the stack again, and I know the stack here ends at 628. So there is the stack frame. And you can see here's the A's, B's, C's, D's. Down here is other letters. Then it has the last two letters and a 0 to terminate it. So my input was not long enough. I did not hit the EIP. All I did was corrupt part of the stored EBP. So this was not enough yet. I need a longer string to take over this machine. So I'll put that in the clipboard, and I'm going to make it a little bit longer. Run. Yes. Put in that junk, and now let's put K, 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 L, 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 L. Okay. Now, let's examine the stack frame again. It goes to 628. I'm going to do info registers to make sure I've got that right. Yeah, EBP is 628. So it goes from here to there. So there, the 4 B's and the 4 C's ended up in my ESP. And I can't remember what it is right off the top of my head, but I can see the end of the string is here. So that must be the L's and the K's. The last 2 K's and the first 2 L's ended up there. I think I know that. So let me just make sure I've targeted it exactly. I'm going to run it again. Yes, I'm going to put in this stuff. And I think these 4 bytes are it. So to test it, I'm going to put in 1, 2, 3, 4. So, and I know 1 in hex is 31, and 2 is 32, and 3 is 33. Those are, if you don't know these things, by the way, just go to a browser and type in ASCII. And you'll find this thing on Google. If you don't know your ASCII, here you go. This is why almost every exploit developer likes capital A, because it's 41. You get used to looking for that. There are t-shirts with 0x41, 41, 41, 41 on them. And the numbers are here. 30 is 0, 31 is 1, 32 is 2. So those are handy things to use when you're going to be looking at both the text and the hex, and you want to not be confused. So if I did this right, this 1, 2, 3, 4 is going to hit the EIP. So let's see what happens. I do info registers to see that the stack ends at 628. Now I examine the stack, and the 628 is here, and it works. That's my 1, 2, 3, 4 in hex, 31, 32, 33, 34. So I now know these bytes right there end up in EIP. Now I'm ready to control the execution and make it go anywhere I want. Now I think I saw a chat message go by. Man ASCII. Yeah, Man ASCII will work in Linux. And the things will be on YouTube by tonight. After class, I'll just load them right up within an hour or 2. All right, good. So that's now I can change the EIP to anything I want. So let's figure out what we might want it to do. I could, I've got a program called main. So I could go to any of these addresses. I could in principle go to addresses in the subroutine, but what I'm going to do here, this program doesn't really have much to exploit. So what I'm going to do is just call the return input again, so it'll print a second copy of the input. That's what they did in your book. It's not very exciting, but there's not much to do here. But to prove that I control the machine, I'm going to call return input again. And let me just check my slides to make sure I'm on the right track, because I tried a couple other things that didn't work. And we did all that, got the crash, we control EIP, and there. Yeah, I'm going to call the return input. So this is the command I want to jump to. Normally it would go to this command and exit, but I'm going to call the function return, hijack the return to repeat the call a second time. So I'll see something happen. So this is the address of my code. Now, there are various ways to make exploits. I like to make them in Python. So let's make this exploit in Python, and we'll build it out of the pieces. So let me get out of the disassembler, if I get to listen to me, okay. And let's make an exploit, which is going to be nano demo.py. Will do, okay. To make a Python executable, you put a shebang and it's /bin and what is it? I'm losing my mind. There. User bin env. Python. All right. Then all I have to do is print this stuff. Now, I need a bunch of this stuff, so I'm going to go get it from my clipboard. Let's go back here. This was the one that worked. So I'm going to put that in my script here. Okay, get rid of the colors there. Now that will put 1, 2, 3, 4 in the EIP and crash. Now I could proceed later, but really I highly recommend baby steps. Do one thing and see if it works. Do one more thing and see if it works. You will get to the end much faster that way. Trying to do 3 steps at once will make you sick. This is why the number one mistake all programmers make is they write too much, too fast. If you write a whole page of code and then you have errors, you don't know where the mistake is. So take one step and test it. Then take one step and test it. So I just want to see if this works. That is my exploit code. So I can run it this way. I'm going to put it in GDB. Well, this one is actually kind of a drag to test, so I'll get to that later in the second half here. Let me start this one the other way. I'm going to go all the way. I normally wouldn't want to do it, but in this case, it's going to take us in a direction I don't want to go. So I just want to find the code I'm trying to execute, which is this one. That's the address I want to make a second call to return input. So what I like to do is put it in my Python in a comment. That's the address I want. So here's how you make an address. I need these 4 bytes backwards in a string. So you put them here, instead of 1, 2, 3, 4, it is \x 7d, \x 88, \x 04, \x 08, escape Y. This is that address, 08, 04, 88, 7d, backwards, 08, 04, 88, 7d. That's how you have to do it. Yeah.
How are you, Darren? So every time you run the program, from what I understand, like you have to use memory.
Yes. That's turned off on this machine.
Okay.
So we're doing an exploit that wouldn't work on any modern system. It'll only work on one 15 years ago. A very good, the fix is you'll be doing it for Linux and Project 10X. It's return-oriented programming. We'll get there. This is the old-fashioned technique that will not work on a modern operating system. For exactly what he said. On a modern operating system, the code relocates every time you run it, so you can't jump to a fixed address like this. What you have to do is you have to jump to code that will jump to some register like ESP. You find like a jump ESP and you go there. That's called return-oriented programming. You bounce off the code so you don't have to know where it is. You use the registers that are already loaded by somebody else. Yeah. That is the neither. It is actually a global option you put in before with an echo statement. It was a system randomization you had to turn off, and it's at the start of the project.
So you set it up.
Yes, yeah. Very good point. You have to turn off the operating system address space layout randomization. And let me point out to it in the project because you've asked it, and it's here we are. What I'm in project 1, which is when you're going to do this. The first thing you have to do is. Not project 1, but project 2, pardon me. There, project 2 is the first one where you do this kind of overflow. And the first thing you do is get rid of ASLR. That is what gets rid of it. You turn off randomized VI space. Then programs will stay in one place and you can do this sleazy stuff. All right, good. And here it said, would that be XD7? I'm not sure what that is. So I don't know the answer. All right. So we're here. Now I put that in. If I've done this right, this program will print the message twice. Yeah?
He's saying like if you change your order of 17.
Oh, yes. Each byte stays in order. So the 7D moves as 7D. Then the next 2 move together. It is not flipping all 32 bits out of order. It's flipping the bytes out of order, but maintaining the order of the bits inside the bytes. That's why it's sort of nuts. This address, you break it into 4 pieces and you put the pieces intact backwards. This is because it's Little Endian. This is big endian. The big thing is on the left, but when you put it in the computer, you have to put the small thing on the left. That's what it is. It's an endianness issue. Yeah. Backslash X means hexadecimal. So you could print a capital A with backslash X41. It just means this lets me print unprintable characters. Good. These are good questions. So there's my demo.py. So now if I run demo.py, let's chmod plus X demo, and now run it. It prints A, B, C, D, E, F, K, and then it prints some unprintable junk at the end. Some of the characters appear as funny symbols. Some of them don't appear at all because those are these funny ASCII hexadecimal codes. But if I print it and then run it through my program, which I think is CH2F, yeah, now it prints twice. So it took the data from this file and printed it, returned, and now went and printed it again because it called the same routine a second time. If I put in something less critical, like if I echo something that doesn't cause the overflow into that program, it'll only print it once. This special string is the attack string, which tricks the program into printing it twice, because these funny characters at the end overwrite EIP. And actually, we're just about to take a break, so for completeness, to solve that question that came up earlier, let's do something awful. Let's turn ASLR back on. If I turn it back on, everything's going to stop working. That turns address space layout randomization back on, and now this one prints once, and that one, it's still printed twice. Wow. Oh, because I compiled it with options that probably tell it not to use it for this program. So I probably have done it redundant. One of those options, no pi or static, might have done the same thing. Anyway, I'm going to leave it off, but I'm not quite sure about those compiler options. Like I said, I used to use no compiler options at all, and then they upgraded Kali to where there's a bunch of this junk turned on, and I'm sort of sloppily attempting to turn it off. Any other questions? I got one here. Should we have access to these files? This is just for demonstration purposes, and you will find them in the PowerPoint. But I haven't made it so you can download them. You can just type them in. Good question. Any other questions? Yeah. You could, but I'm just using Kali. So I recommend using Kali because it's the standard for all our other classes, and I'm writing the project so they work in Kali. The only difference is you have to put the no pi and the static compiler option to tell it not to use the advanced features. They are in the book. Yeah, they're also in the book. That's right. Okay, you can download them from the textbook. All right, well, it's about 2. Let's take a break and pick up at 2:05 so people get a 10-minute break. And I'll start another Zoom session after that. Good, we don't have an unwieldy number of people. And then I'll just demonstrate the project that goes with this.